Welcome to the fourth part of thermodynamics. In this part, you will learn about specific heat capacity and Maier's relation. There are some important things to remember about first law of thermodynamics. Delta Q or Q is positive when heat is given to the system, and from when taken, delta Q will be negative. Work done is positive when the system expands and does work on the surroundings. Hence, we may say that when a certain amount of heat is given to the system, then some part of it is used in increasing the internal energy, while remaining part leaves the system in the form of work done by the system on the surroundings. And from equation 4, we can see that first law of thermodynamics is a statement of conservation of energy. Stated as the energy put into the system equals the sum of work done by the system and change in its internal energy. And when delta U is 0, then obviously Q will be equals to W. If system reach from state A to B by executing number of steps, we can write the change of internal energy between state A and B as delta U is equals to Q1 plus Q2 plus Q3 minus W1 plus W2 plus W3 and so on. And if the system returns to its original state after executing number of steps, then obviously delta U will be 0. And the sum of the Q's 1, 2 and 3 must be equals to the work done W1, W2 and W3. Specific heat capacity. It is the amount of heat required to raise the temperature of a body per unit mass. It depends upon the nature of substance temperature. It is denoted by small s, and in mathematical form it is delta Q divided by m into delta T, where m is the mass of the body, delta Q is the amount of heat absorbed or rejected, and delta T is the temperature change. So its unit will be joule per kilogram per Kelvin. Suppose an amount of heat delta Q supplied to a substance to change its temperature from T to T plus delta T, then heat capacity will be delta Q divided by delta T. A different amount of heat may be needed for a unit rise in temperature at different temperatures. And to define a constant characteristic of the substance independent of its amount, we should divide S by the mass of the substance in kilogram. So small s is capital S divided by m, means delta Q divided by m into delta T. And this S is known as specific heat capacity of the substance, which depends upon the nature of the substance and its temperature, and the unit is joule per kilogram per Kelvin. Here is a specific heat capacity of water. Earlier, 1 calorie was defined to be the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. With more precise measurements, it was found that specific heat of water varies slightly with temperature. And the variation is shown in the following graph. For a precise definition of calorie, it was therefore necessary to specify the unit temperature interval. So 1 calorie is defined to be the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. In SI unit, the specific heat capacity of water is 4186 joule per kilogram per Kelvin. That is 4.186 joule per gram per Kelvin. And you know, water has highest specific heat capacity. And because of its this property, it is used as a coolant in automobile radiators and in hot water bags. The specific heat capacity depends on the process under which heat capacity transfer takes place. For example, for gases, we can define two specific heats: specific heat capacity at constant pressure. In this, if the gas is held under constant pressure during the heat transfer, then the corresponding molar specific heat will be molar specific heat capacity at constant pressure. And it is denoted by a symbol C with subscript P. Similarly, if the volume of the gas is maintained during the heat transfer, then the molar specific heat capacity will be the molar specific heat capacity at constant volume, denoted by C with the subscript V. Let's derive a relation between these two molar specific heats. For 1 mole of a gas, from first law, delta Q is equals to delta U plus P delta V. If delta Q is absorbed at constant volume, then delta V will be 0 and delta Q will be equals to delta U. Then the CV will be equals to delta Q by delta T with a subscript V, means at constant volume, and it will be delta U by delta T at constant volume. We can drop the subscript V in the last step because we know that the internal energy of an ideal gas depends only on temperature. Now consider delta Q is absorbed at constant pressure. So delta Q by delta T at constant pressure will be delta U plus delta T at constant pressure plus P delta V divided by delta T at constant pressure. Again, the subscript P is dropped from the last term. So Cp minus Cv will be equals to P into delta V by delta T at constant pressure. Now for 1 mole of a gas, PV is equals to RT. On differentiating it with respect to temperature for constant pressure, you will get P delta V divided by delta T at constant pressure will be R. So Cp minus Cv is equals to R, and it is also known as Maier's formula. And the ratio of the two specific heats Cp by Cv is denoted by gamma.